Okay, folks, welcome back. Just a quick note before we get started with continue with our discussion of the bonding interactions here. I posted on Classroom for you a table that you can use to help you with the geometries, with the electron geometry and with the molecular geometry. So please take a look at that to help you with kind of understanding what you have to do and what the interactions are that explained in Vesper theory. So I posted it on Classroom for you. Please take a look at that. And if you have any questions, please email me and let me know. And if I have to, I'll arrange a time to meet with you guys and we'll talk about it live. Okay. Um, all right. Let's go ahead. Let's continue where we left off with yesterday. Now we were talking about the interactions here. Now understand we've talked about the hybridizations. We've talked about two types of hybridizations, and a hybridization, remember, is an orbital that forms when atoms get together to form a molecule. So when separate atoms get together to form a molecule, they rearrange, they kind of redistribute their electrons, form different types of orbitals. And so with the atomic orbitals, we have the s, the p, the d, and the f orbitals. And so that's when the atom's all by itself. It has these atomic orbitals that basically are just the probability of finding electrons at certain energy levels and around a particular atom. However, when atoms get together to form compounds, when atoms get together to form specifically molecular compounds, and they have to share their electrons share the electrons with another atom, they have to reconfigure those orbitals. And so in reconfiguring those orbitals, they form then these hybrid orbitals that occur in the compound itself. So the atom then reconfigures its orbitals to form these hybrid orbitals. And from these hybrid orbitals, then they can go ahead and share their electrons with another atom. And so with the way that they share them, so that's where we're picking up with here. There are different ways that the atoms can share their electrons. And we saw them with methane. Basically with methane, the sp3 orbital of carbon, the sp3 orbital of carbon basically shares its electron with the s orbital of hydrogen. And keep in mind, remember, hydrogens do not hybridize. Hydrogen atoms do not undergo hybridization because they only have, hydrogen atoms only have that one electron, and so it doesn't need to undergo hybridization. But we saw that with this bond here, with this bond between carbon and hydrogen in methane, this was a bond that forms when the sp3 hybrid orbital from the carbon overlaps with the s orbital from hydrogen. The electrons then, the two electrons then move between them, and that hybridization occurs, that overlap occurs between an sp3 orbital from carbon and an s orbital from hydrogen. So this is from carbon here. This is your single electron from carbon. This is going to be your electron from the atom of hydrogen. So this is an s orbital, unhybridized atomic s orbital, and this is an sp3 hybrid orbital here. We said then that the line, you can draw a line essentially through that interaction. Okay, and so this interaction between these two orbitals here is what we refer to as a sigma bonding interaction. So it's a sigma bonding interaction. And so this interaction then explains how the electrons will be shared between a sp3 hybrid orbital and an s orbital from hydrogen. So this is from the carbon and this is from the hydrogen. This is the bond that we're talking about. So this is a single bond that is sigma, that has a sigma interaction. Okay, so we can describe this bond then as a single bond. Single bond, why? Because you only have two electrons being shared between those two atoms. So it's a single bond, and it has a sigma interaction. It's sigma bonding interaction. So that's how we can characterize this bond now. So now we can go ahead, using our knowledge and understanding of hybridization, we can then now describe then each bond then as either each bond by the number of electrons that are being shared and how those electrons are being shared. So this first one tells us the number of electrons being shared, and then the second one here is how those electrons are being shared. Okay, so we can describe it in both those terms, and we did that. And let me go ahead and I did that for you yesterday. Okay, and so let's go ahead then and let's take a look at where we left off with. Okay? And so with that said, then we saw then that there is a sigma interaction here between each one of these. And so make sure you understand that each of these sp2 hybrid orbitals now, and so remember, we know that the hybridization here for a double bonded carbon is sp2 because the bond angle is here. The bond angles now, not the bond angles are going to be 120, but the shape then, both electron and molecular geometry here is going to be trigonoplanar. And so that's why it's useful to make sure you do that. Make sure you go back and take a look at that table that I set up for you. But the reason why we know that the hybridization for this carbon is different, and again, let me re-emphasize, hydrogen does not undergo hybridization. And so when we talk about hybridization, we're referring to the hybridization of the carbon here. So we know then that the hybridization of the carbon is different here than in methane because of the shape of the molecule. Folks, hopefully by the end of the discussion today, you can make that connection between the shape of the molecule and the type of hybridization. Okay? And I'll recap that for you as well. Okay, but make sure you understand then that the shape of this carbon here, the electron and molecular geometry of this carbon is going to be trigonoplanar, with the angles here between the bonds being 120. And so with that said, then this carbon then is sp2 hybridized, and sp2 hybridization, remember, is an s orbital being hybridized together with two p orbitals to give you three sp2 hybrid orbitals and one unhybridized p orbital, and that's how we obtain sp2 hybridization. Okay. All right, so each carbon then has three sp2 hybrid orbitals and an electron in each one of those. The fourth electron for carbon, the fourth valence electron for carbon, will fall into that p orbital. And remember, the three sp2 hybrid orbitals are degenerate, meaning that they're all equal in energy, but this one electron here in the p orbital is going to be slightly higher in energy because it is not degenerate. P orbitals are going to be higher in energy than s orbitals. P orbitals then will be higher in energy than sp2 hybrid orbitals. Okay? All right, so there are your four electrons. And so when this bond forms here, and we already talked about that, we saw that on the previous slide, I was using that to review with you. This is a single carbon hydrogen bond. That single bond then is going to be two electrons being shared between these two atoms. And so therefore this interaction here is going to be a sigma interaction. It's going to be a sigma bonding interaction because you have an overlap. You have an overlap between an sp2 hybrid orbital this time and an s orbital of hydrogen, but that overlap falls along a straight line, meaning you can draw a straight line through that interaction, and that's a sigma interaction here. That will be true for all of these single bonds here. Each one of these single bonds here will be an sp2s interaction, which is going to be sigma bonding. Okay, sigma bonding. Now, with that said, then let's take a look at these two bonds here. So that's, we've accounted for each one of these single bonds here. What about this double bond between the carbon and each of the carbons? Well, first of all, you're going to see then that there's going to be an overlap between the sp2 hybrid orbital. So each carbon is going to take two of its three sp2 hybrid orbitals to interact with the hydrogen in each of these sigma bonds here. The third of those sp2 hybrid orbitals will form one of these bonds here. And if you look at this table here, you'll look at this diagram, you'll see then that there's an overlap here between the sp2 hybrid orbital from this carbon and an sp2 hybrid orbital from the carbon on the right. And that interaction, that overlap then is going to be very similar to this overlap here, where you could draw a straight line through that overlap. And so therefore this also is a sigma bonding interaction. And so it could have been either one here in the diagram, but I arbitrarily chose to show you then that this bond here of the double bond, this bond here of the double bond will be sigma bonding interaction. Why? Because the two sp2 hybrid orbitals here, okay, are overlapping each other in such a way where they fall along a single line right there. So that's sigma bonding interaction. So what about the other bond of the double bond? Well, that's how these two electrons are being shared. But remember, each carbon also has an electron in the p orbital. So these two electrons here that are in the p orbitals, they will interact with one another. They will interact with one another to form this bond here. This bond is the sharing of this electron and this electron here. These two electrons are in the p orbitals. If you notice then, when the p orbitals when they get together, they are lined up side by side. There's this side-by-side interaction instead of a head-on straight line interaction. You have a side-by-side interaction. That interaction is what we refer to as a pi bonding interaction. Okay, And so whenever you have two orbitals that are lined up side by side, that is a pi bonding interaction. And so the second of the double bond is not a sigma bonding interaction, but it's a pi bonding interaction. And that's where we left off with yesterday. And that's where we left off with yesterday. And that's where I want to continue with today, just to finish up here for you. Okay. All right. So with that said, then this diagram here shows us a little bit better the interaction that I've been talking about. Okay. And so what we have here, and let's just take a look at this here really quickly. Okay. Here we have this is each one of these here is the carbon. Each one of these here represents the carbon hydrogen single bond. This is the carbon hydrogen single bond. Each one of these here are the carbon hydrogen single bonds that is represented in this interaction here. So it's a single bond. Why? Because you have two electrons that are being shared between each of the atom, between the carbon and each hydrogen. And it is going to be a sigma interaction here. This is a sigma interaction. Why? Because you have in each one of these interactions here, you can draw a straight line. You can draw a straight line that runs through both orbitals, that splits it in half essentially. Okay? And so that's why each one of these, so this is going to be an sp2, and if you notice here, each one of these single bonds here is an sp2s interaction. This is an sp2s interaction, meaning then it's an interaction between an sp2 hybrid orbital and an s orbital from hydrogen, sp2 hybrid orbital from carbon, and an s orbital from hydrogen. So therefore, it's an sp2s interaction that is single bond. That is a single bond. That is a sigma bonding interaction. Okay? So this sigma bonding interaction is between an sp2 hybrid orbital and an s. Okay, so we've now characterized each one of these bonds here. This interaction here is also sigma bonded because you can draw a line through it, and this represents one of the bonds of the carbon-carbon double bond. So one of the bonds in the carbon-carbon double bond will be a sigma bonding interaction that is not sp2s, but it's going to be an sp2 sigma interaction. Okay. Why? It's the interaction, the overlap between two sp2 hybrid orbitals, and that interaction accounts that is a straight line that you can draw through it. So this is also going to be a sigma bonding interaction there. Okay. Okay. So with that said, let's go ahead and take a look at the pi bonding interaction that I was referring to. Okay. So with that said, then. And I've highlighted for you here in this drawing here, there is your sigma bonding interaction there. Okay, so that represents the single bond, one of the bonds between carbon-carbon. Okay, and now remember, there is the fourth electron from each one of these carbons that sits in the p orbital here. That interaction here, and that's the interaction we're going to talk about, right? That is sharing right there. That represents a side-by-side interaction. So therefore, this is a pi bonding interaction. This is your pi bonding interaction, okay? Because each one of these electrons now will be shared between these two p orbitals. So these are p orbitals here. These are not hybrid orbitals. These are unhybridized atomic orbitals. But the electrons are shared between them. Now, the electrons can be here in this space here, or they can actually be down here as well. But the second of the double bond, then is going to be your pi bonding interaction. So you have one sigma, okay, and you have one pi. So this interaction here is going to be the sigma interaction here between the sigma bonding interaction, and this interaction here, as we pointed out here, is your pi bond. So in a double bond, one of those bonds is going to be a sigma bonding interaction, and the other one is going to be your pi bond. Okay. Okay. All right, so that's what we have for a double bond. So for single bonds, for whenever you have a single bond that is just two electrons that are shared between two atoms, that will always be a sigma bonding interaction. Because sigma bonding interaction accounts for the interaction between two atoms sharing two electrons. That is your sigma. That's your single bond. When you have a double bond, though, in a double bond, one of those bonds of the double bond, two of those electrons will be shared in a sigma interaction manner, and the other one will be shared in a pi bonding interaction. Okay, so that's what you have to make sure you keep in mind when you go through this. Okay, all right, very good. Let's go ahead then. Okay. And let's just quickly review then what we have here. And so there it is. What I've laid out for you then here is all of the bonds that you see, and we can characterize every single bond now. In the ethene, in the ethene molecule here, we can characterize each one of those each one of those bonds. And that's the whole idea behind doing this. We can now describe what the bond is, single, double, or triple. And then now we can also describe the type of interaction that occurs in that particular bond. Okay? So we have here then, this is our signal interaction. This is the single bond here. And I'll leave it up to you to see that. We have the single bond here. It's a single bond, so that's going to be sigma. It's the interaction between an s orbital of hydrogen and an sp2 hybrid orbital from carbon, and that accounts then for each one of these carbons here. For the double bond then, we see then, in this double bond here, we see then that one of those bonds is a sigma interaction, so two electrons will be shared in a sigma bonding interaction between two sp2 hybrid orbitals, and the second pair of the double bond is going to be shared as a pi bonding interaction between two p orbitals from the two carbon atoms. And so this is how now we can characterize the double bond between the two carbon atoms. Yep. All right, very good. So let's go ahead then. So we've talked about sp3, we've talked about sp2, and let's talk about real quick about sp hybridization here. Okay. So with sp hybridization, and if we can just quickly go through this, then with sp hybridization, what we're looking at then is the interaction between one s orbital. So from one s orbital combined together with one p orbital to give us then two sp hybrid orbitals, which means then you will have then, so let's just you'll have then remaining a and I'll just arbitrarily call this the z and the y axis here. Okay? You'll have two unhybridized p orbitals. Okay, so with that said, then when you can combine together one s orbital with one p orbital, then you'll have an sp hybrid orbitals, and you'll form two of those, and you'll end up with the three p orbitals here. You end up with two sp hybrid orbitals and two unhybridized p atomic orbitals. Okay. All right, so with that said then, what we're going to see then is if we, with sp3 hybridization, we saw a tetrahedral configuration arrangement of those orbitals. With the sp2 hybridized orbitals, we saw a trigonal planar. With an sp hybrid orbital, we're going to see a linear arrangement of these orbitals here. Okay? So you want to keep that in mind as we move forward with this. So you'll get two sp hybrid orbitals, and if you notice, the shapes here are very similar to what you saw here. The hybridized shapes will always be fairly similar to one another, but this time though they will assume 180 degrees when they line up. Okay. Okay. So let's go ahead then. Okay. All right. And just like with the when we talked about with the other hybrid orbitals, the two sp hybrid orbitals, they will be degenerate. They will be equal in energy here, but the two remaining unhybridized p orbitals, they'll be higher in energy. Okay, so you have two atomic orbitals that are higher in energy than the two hybridized orbitals here. So they're going to be lower in energy and than the two p orbitals. So let's go ahead then and okay, let's take a look at carbon dioxide and analyze here the structure for carbon dioxide and take a look at it. Okay. All right. So I'm not going to ask you to draw it. I think you can draw it on your own. But with carbon dioxide, then with the carbon atom here, you have then two double bonds, and we're going to see then that the carbon atom then is going to be sp2 hybridized, which means then you're going to have let's take a look at this here. You have your two sps, so this is going to be an sp hybridized orbital here, and you have an sp hybridized orbital here. Now, I would be curious to ask you then, so the carbon atom here is sp hybridized here. Okay, I just want you to quickly take a look at oxygen. Okay, take a look at oxygen here, and you tell me what's the hybridization of oxygen. Real quick, just go ahead and answer for yourself. And if you need to write it down on a piece of paper, if you need to go through the steps, answer it. What is the hybridization of the oxygen? Okay. All right, well, let's go ahead and let's take a look at this. Well, let's first of all count. Remember, when we do this, we need to determine, when we determine the hybridization of an atom here, we need to count the electron domains first. Okay, we need to figure out the geometry of those electrons. Okay, and so we have then here 1, 2, 3 electron domains. We have 3 electron domains for oxygen. Remember, when you have 3 electron domains, whenever you have 3 electron domains, and let's go ahead and this is why you need to review this for VSEPR, you guys. Okay, when you have 3 electron domains, and for each oxygen here, we have then 1 bonding. Okay, we have 1 bonding and 2 non-bonding. And this is, again, we are characterizing the oxygen atom here, you guys. When you have 2 bonding and 2 non-bonding, therefore with 3 electron domains, the electron geometry for that one is going to be, then remember, trigonal planar. Trigonal planar. Now, obviously, the molecular geometry for this one, since it only has 1 bond, it's going to be linear, obviously. We already saw that. But this is what we need here. We need then that electron geometry. Why? Because with that electron geometry, you can imagine then that the spacing, the angle between each one of these electron domains is going to be 120. And with a 120 electron domain, or if you want to think about with the trigonal planar electron geometry, the hybridization then is going to be sp2 hybridized. So each oxygen then is sp2 hybridized here. So this is sp2, and this is also sp2. Remember, I had pointed out to you when we talked about electron geometry and we talked about VSEPR theory, that when we characterize the geometry of a molecule, we're looking at the center atom. We're looking at the geometry of the center atom. However, I did tell you that we can characterize the geometries of any atom, and we can do that by just counting electron domains. And in this instance here, why do I point that out to you? Because you have to recognize here that the interaction here between the oxygen and the carbon, between each oxygen and the carbon here, is going to be between an sp2 hybrid orbital and an sp hybrid orbital, and this one here is going to be a pi orbital interaction. Okay? And that's what I want to point out to you, and we'll pick up with this tomorrow, but do keep this in mind that the interaction here is going to be important for us because, the characterization of the oxygen atoms here will also be important to us because the bonds here is a bonding interaction between an sp2 hybrid orbital and an sp hybrid orbital that is along the line. So one of these would be sigma, but the other bond, which is a pi bond, will form between the side-by-side interaction between the p orbital from this oxygen and the p orbital from this oxygen. And you would not be able to recognize that there's a p orbital here on this oxygen unless you can first and foremost identify that it is sp2 hybrid. Okay? Because remember, with an sp2 hybrid or with an atom that is sp2 hybridized, one of those p orbitals is unhybridized. And so we'll finish this analysis here of the bonding in carbon dioxide tomorrow. But please do keep in mind then that, and I'll review this for you, you have to be able to characterize the geometries of each one of these, of all the atoms here as well. So take a look at that table that I posted for you on Classroom. Use the PhET Lab to help you familiarize yourself and become more comfortable with hybridization, the geometries, because the geometries are absolutely important. They are connected. They are tied in with this discussion of hybridization. Okay. All right. So what I'm going to do is I'm going to stop right there, and then we'll pick up this discussion tomorrow. Please start taking a look at the molecular orbital theory, which is going to be section 9.2, and we'll pick up with that discussion. And I would like to do that starting tomorrow. Okay. All right, folks. Have a good day, and I will we'll pick up with this discussion.